Relations and functions. In our everyday life, we come across many relations between people and people, people with objects and objects with objects. In mathematics also, there exist relations such as parallel lines, perpendicular lines, number 2 less than 5, A is a subset of B. A relation is just a set of ordered pairs. Let's define what you mean by an ordered pair. Have a look at these combinations: mobile SIM card, television remote, monitor CPU. These form ordered pairs. Also, mobile, television and monitor form an ordered triplet of electronic gadgets and SIM card. Remote and CPU form another ordered triplet of the accessories without which electronic gadgets won't work. These are all examples of ordered pairs. Ordered pair. An ordered pair consists of two objects or elements in a fixed order. It is written in the form shown where A and B are called the first component and the second component of the ordered pair respectively. Remark: two ordered pairs are equal if and only if the corresponding first elements are equal and the second elements are also equal. If the ordered pairs of A, B and X, Y are equal, then it implies A is equal to X and B is equal to Y. We know that a set is a collection of well-defined elements. So, let's study what are relations in sets. For this, we define a term Cartesian product. In the combination of mobile SIM card, television remote, monitor CPU, the Cartesian product is mobile SIM card, mobile remote, mobile CPU, television SIM card, television remote, television CPU, monitor SIM card, monitor remote, monitor CPU. So, the Cartesian product of two non-empty sets, A and B, is defined as the set of all ordered pair of A, B, where A belongs to A and B belongs to B. It is denoted by A cross B. Example: if A is a set of two elements, 1 and 2, and B is a set of A and B, then the Cartesian product is a set of ordered pairs of elements of both A and B. The Cartesian product of three sets is denoted by A cross B cross C and is defined as shown. Remember, the Cartesian product of two sets A and B is a null set if either A or B is a null set. If A and B are two sets such that none of them is a null set, then the Cartesian product of A with B is not the same as the Cartesian product of B with A. If there are X elements in A and Y elements in B, then the Cartesian product of A and B will have X, Y elements. See this example. If A and B are two sets with their elements as shown, then their Cartesian product is a set of four ordered pairs as shown. This can be verified. Since set A has two elements and set B also has two elements, so their Cartesian product will have 2 multiplied by 2, that is 4 elements. If set A is equal to the set B, then their Cartesian product will be either A square or B square. The Cartesian product of A and B is an infinite set if either A or B is infinite. After going through this module, we will be able to understand and learn basic concepts, relation, functions, some functions and their graphs, algebra of real functions, and the summary. Now let's understand what a relation is. If A and B are two non-empty sets, then a relation represented as R from set A to set B is a subset of Cartesian product of A and B. The subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. The second element is called the image of the first element. Remark: the total number of relations that can be defined from a set A to a set B is the number of possible subsets of the Cartesian product of A and B. If the number of elements of A is x and the number of elements of B is y, then the number of elements of the Cartesian product is x, y, and the total number of relations is 2 raised to the power x, y. If the ordered pair A, B belongs to relation, then we say that A is related to B, and if the pair does not belong to the relation, then A is not related to B. Types of relation. First one is the empty or null set. If R from A to B is phi, then the relation is known as empty or void relation. Next is the universal relation. If A and B are two non-empty sets and a relation R from set A to set B is a subset of Cartesian product of A and B, then the relation is known as universal relation. Let's now see how we can represent a relation. A relation can be represented algebraically in two ways: by roster method and by set builder method. Roster method. In this form or method, a relation is represented by the set of all ordered pairs belonging to R. Look at this example. If R is a relation is greater than from A to B, where the sets A and B are shown, then find R in the roster form. We can see from the solution that the relation is a set of 6 ordered pairs following the condition of greater than given in the question. Next is the set builder method. In this form, a relation R from set A to set B is represented as shown. Have a look at the example. If two sets A and B are given and also the relation R is given, then R can be described in set builder form as shown. Arrow diagram. An arrow diagram is a visual representation of a relation. In order to represent a relation R from a set A to a set B by an arrow diagram, draw arrows from the first components to the second components of all ordered pairs belonging to R. For example, the relation R, which is defined as A is greater than B, is represented as shown by the arrow diagram. Now let's define domain of a relation. The set of all first components of the ordered pairs in a relation R from set A to set B is called the domain of relation R. Range of a relation. The set of all second components of the ordered pairs in a relation R from set A to set B is called the range of relation R. Codomain of a relation. For any relation R from set A to set B, the whole set B is called the codomain of the relation R. Look at this example. Let R be the relation from A and B, which is defined as A is greater than B. Then the solution set or the set of ordered pairs of R is as shown. Also, the domain of R is a set of the first components of the ordered pairs in R. So, the domain is a set of 3, 4, and 5. The set of second components of the ordered pairs in R is called the range of R. So, range is a set of 1 and 2. The second set B is called the codomain of R. So, codomain is a set of 1 and 2, that is same as B. If we look at our previous example of combinations of ordered pairs of mobile SIM card, television remote, monitor CPU, then mobile, television and monitor form the domain and SIM card, remote and CPU form the range. Now let's define inverse of a relation. The inverse of a relation is just the exact inverse of the ordered pairs of the original relation. Let A and B be two sets and R be a relation from set A to set B. Then the inverse of R, denoted by R raised to the power minus 1, is a relation from B to A and is defined as shown. So the domain of R inverse would now be given by the range of R and the range of R inverse by domain of R. Have a look at this example. Let A and B are two sets as shown and the relation R is defined as shown on the screen. Now in order to find the inverse of this relation, all we need to do is flip over each of our ordered pairs. So when we open up the set, we take the first ordered pair 3, 1 and flip it, which gives 1, 3. Similarly, we do for other ordered pairs and obtain the inverse. We can also find the domain and range of the inverse relation as shown. Have a look at this printer. What is its function? A blank sheet is inserted into the input slot and a printed sheet comes out as the output. Now let's understand the concept of a function. A function is a relationship between any two sets of numbers. Let A and B be two non-empty sets. Then a function f from set A to set B is defined as a method that relates the elements of set A to the elements of set B such that all the elements of set A are related to the elements of set B. An element of set A is related to a unique element in set B. It is denoted as shown, where B is called the image of A under F and A is called the pre-image of B under F. Points to remember. All functions are relations, but the vice versa is not true. We may think of this as a mapping. A function maps a number in one set to a number in another set. A function maps values to one and only one value. That is, for every input there is one and only one output. Two values in one set could map to one value, but one value must never map to two values. That would be a relation, not a function. Have a look at the example. A function is defined as f(x) is equal to x squared. Then the mapping is done as shown. This function f maps numbers to their squares. Let us now define the domain, range and codomain of a function. Let f from A to B be a function from set A to set B. Then the set A is known as domain of f. The set B is known as the codomain of f. The set of all the f images of the elements of A is known as the range of f. Look at this example that we discussed earlier. By looking at the mapping, we conclude that the domain is equal to the set A and the codomain as well as the range is equal to the set B. Real valued function. A function which has either R, the set of real numbers, or one of its subsets as its range is called a real valued function. Real function. A function which has either R, the set of real numbers, or one of its subsets as both its domain and range is called a real function. Scope and excitement of physics. Physics deals in various subdisciplines such as mechanics, optics, heat and thermodynamics, electrodynamics, atomic physics, nuclear physics, etc. Basically, there are two domains of interest, macroscopic and microscopic. Macroscopic. The macroscopic scale is the length scale on which objects or processes are of a size that is measurable and observable by the naked eye. Classical physics mainly includes macroscopic phenomena. Microscopic. The microscopic scale is the length scale on which objects or processes are of a size that is measurable with the help of a lens or a microscope. Quantum theory is currently accepted for explaining microscopic phenomena. There are various types of functions: identity function, constant function, polynomial function, rational function, modulus function, signum function, and greatest integer function. Let's discuss them one by one. The first is the identity function. A function f shown is known as an identity function if f(x) is equal to x for all x belongs to R. Domain is the set of R of all real numbers. Range is the set R of all real numbers. Next is the constant function. If a is a fixed real number, then a function f shown is given by fx is equal to a for all x belongs to R. Domain is the set R of all real numbers. Range is the singleton set A. Polynomial function. A function f of real numbers is known as a polynomial function if for each x in R, fx is equal to the series shown, where n is a non-negative integer and a0, a1, a2 up to an belongs to R. The function f of real numbers given by fx is equal to x square x belongs to R is a polynomial function. Domain is the set R of all real numbers. Range is the set of all non-negative real numbers. Next is the rational function. Rational functions are functions of the type fx by gx, where fx and gx are polynomial functions of x defined in a domain where gx is not equal to 0. The function shown is a rational function. Domain is the set R of all real numbers except 0, that is R minus 0. Range is the set R of all real numbers except 0, that is R minus 0. Modulus function or absolute value function. The modulus function f of real numbers is defined by fx is equal to mod x, which is x when x is greater than equal to 0 and is minus x when x is less than 0. Domain is the set R of all real numbers. Range is the set of all non-negative real numbers. Signum function. The signum function f of real numbers is defined by fx is equal to 1 if x is greater than 0, 0 if x is equal to 0, and minus 1 if x is less than 0. Domain is the set R of all real numbers. Range is the set of minus 1, 0, and 1. Greatest integer function or the step function. The function f of real numbers is defined as shown, where x belongs to R, assumes the value of the greatest integer less than or equal to x. Look at the values of x for various intervals. Domain is the set R of all real numbers. Range is the set of integers shown. Algebra of real functions. Let f and g be any two real functions as shown, where x is a subset of R. Then we define addition of two real functions as shown, subtraction of a real function from another as shown, multiplication of two real functions as shown, quotient of two real functions. The quotient of f by g, denoted by this expression, is a function defined as shown, provided g of x is not equal to 0 and x belongs to x. Multiplication by a scalar. Let f be a real valued function and alpha be a scalar. Then the product alpha, f, is a function from x to r defined by alpha f of x is equal to alpha into f of x, where x belongs to x.
Let us summarize what we have learned.
Ordered pair. An ordered pair consists of two objects or elements in a fixed order. It is written in the form shown, where A is called the first component and B is called the second component. Cartesian product. The Cartesian product of two non-empty sets A and B is defined as the set of all ordered pairs A, B, where A belongs to A and B belongs to B. It is denoted by A cross B. Relation. Let A and B be two sets. Then a relation R from set A to set B is a subset of A cross B. Domain. The set of all first components of the ordered pairs in a relation R from a set A to a set B is called the domain of relation R. Range. The set of all second components of the ordered pairs in a relation R from a set A to a set B is called the range of relation R. Codomain. For any relation R from a set A to set B, the whole set B is called the codomain of the relation R. Inverse relation. Let A and B be two sets and R be a relation from set A to set B. Then the inverse of R, denoted by R raised to the power minus 1, is a relation from B to A and is defined as shown. Function. A relation f from a non-empty set A to a non-empty set B is said to be a function if an element of set A is associated to a unique element in set B, all elements of set A are associated to the elements of set B. Algebra of real functions.